says a metal block of mass 5 kg lies on a rough horizontal platform. So let's say this is the horizontal platform, and the metal block has mass 5 kg. If a horizontal force of 8 Newton is applied to the block through its center, so a force of 8 Newton was applied through its center, that's like center of mass. That's also another thing to discuss some other time. Why was the force applied through its center? We'll talk about that one too. If a horizontal force of 8 Newton applied to the block through its center of mass, in fact, you see, I've not finished the question, but I already talked about center of mass. Why will you choose to apply force to an object at its center of mass and not just anywhere on the body? This is also something we'll talk about, but not today. Just slide the block on the platform, then the coefficient of limiting friction between the block and the platform this is also very, very simple. The coefficient of limiting friction is also the same thing as coefficient of static friction. When you hear static, think of limiting. When you hear dynamic, think of kinetic. So we're looking for the coefficient of limiting friction, that is when the body has not started moving. And if the body will start moving, then you have to overcome this frictional force first. So our mu equals to what? Our Fr equals to mu r. So mu equals to Fr over normal reaction. So this is very simple. So our mu equals Fr over normal reaction. Now, but this 8 Newton that was given here is not the frictional force. But we need the frictional force, of course. We can know the normal reaction already. That's mg, that's 5 times 10, that's 50. But let me now tell you why 8 Newton will be our frictional force. Let's read the question again. The question says a metal block of mass 5 kg lies on a rough horizontal platform. If a horizontal force of 8 Newton applied to the block through its center of mass just slides the block on the platform, which implies that what? It did not accelerate, it did not give it more, it did not make it accelerate more, it just slides it. And I already said that whenever you're talking about a force that will just slide an object, a force that will just set a body ready for motion, then such force will be equal to the frictional force that was previously on the body. So which implies that our frictional force here will be the same thing as that force. So we have our mu to be what? 8 over what? 5 times 10, that's 50. And what's 8 over 50? I'm going to use my calculator for that. So 8 divided by 50, that's 0.16. So mind you, coefficient of friction does not have units, so we have 0.116, and that solves that problem quite easily done. Now let's take another question. Okay, this question we have here is just like the diagram I drew the other time, but now we'll see it in application. Let's see what happens here. We have a diagram of an object. This object is of mass 2 kg. Of course, there's a pulley here, a string, and another mass that is hanging. This one is 4 kg mass. Let's read. A mass of 2 kg on a surface where the coefficient of friction is 1 over 2. So this surface is actually a rough surface. So we have our mu to be 1 over 2. It's connected to a second mass 4 kg over a frictionless pulley. That is, this pulley is frictionless, which means that we don't have to bother ourselves about this pulley. This pulley is just allowing the object to roll, the string to be able to roll. So there's no friction there. It's not contributing to what is happening here. So over a frictionless pulley as shown in the diagram, if the acceleration due to gravity is 9.8 meters per second square, then the masses will. So we are trying to look for what will happen to these masses. You know, like I said the other time, I said two things can happen. This mass can cause this thing to do something. It can either cause it to accelerate or just remain like that or not have effect on it at all. And I said this one does not have any effect. So if there's going to be an acceleration, then this guy will be the one causing the acceleration. Now take note of that. So in this place we are given g to be 9.8 meters per second. In fact, 9.8 meters per second squared. So the question, let me read the option. The option says that the masses will accelerate at, of course, they will have the same acceleration. The acceleration of this one will be the same acceleration. The option here says that the masses will accelerate at 4.9 meters per second squared. I don't know. B says remain stationary. C says accelerate at 9.8 meters per second. And D, E, blah 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 like that. All of them are talking about acceleration, which means that this question is actually interested in me finding the acceleration of these masses. What happens to them? Do they accelerate? Do they remain stationary? So let me find out what's happening here. Now from that, I can start with this one first. You know, there will be a tension in this string and there will be a tension here. Of course, the weight of the object, which is going to be 4 times 9.8. 4 times 9.8. And the weight of this object is 4 times 9.8. So let me do this. This will be T minus frictional force equals MA. That's our M1. And what's our T? T, we don't know T. So we have T minus, what's the frictional force? That's mu mg. So that's mu is 1 over 2 multiplied by, what's the MA? We have mass to be 2, then times what? Times 9.8. That will be equals 2 times the acceleration. So we can call this one equation 1. By the time we simplify our equation 1, we have T minus 9.8 equals 2a. Now let's take the second case as well, which is this axis. So we will have 4 times 9.8. 4 times, let me use my calculator to calculate. 4 times 9.8, that's 39.2. So we have 39.2, which is the weight, minus the tension, will be equals to 4 times the what? Acceleration. So this is equation 2. Now I'm looking for my acceleration. So if I have two variables, tension and acceleration, and I have two equations, that's sufficient enough for me to solve for T and A. So I don't need T, let me just solve for A. So I can put this equation here. This will be T minus 9.8 equals 2A. So this is our equation 1. You realize that if I add these two equations, then my tension will be given up because I have a negative tension here and I have a positive tension here. So since it's the same tension, if I add the two equations, then tension will be 0. Then this will be 39.2 minus 9.8. So 39.2 minus 9.8, that gives 29.4. 29.4 equals 6a. So which implies that acceleration equals 29.4 divided by 6, and that's 4.9. So that's 4.9 meter per second square, which implies that the masses actually accelerate, and the acceleration is what? 4.9 meter per second square. So that's option A. The masses will accelerate at 4.9 meter per second square. So that's the end of that question. Let's take another one. Now this one is similar to what we just saw finish here, but it's like a derivation. So let's see how we can go about it. We also have masses M1, we have M2 here, we have M1 here. So in the diagram above, the angle mass M2 is adjusted until M1 is on the verge of sliding. On the verge of sliding. That means that it's almost sliding. The coefficient of static friction between the mass M1 and the table is. So we are looking for the coefficient of static friction. That's what we are looking for. So let's write our equations out. I won't waste much time on that. You know that since there's friction on this surface, then we have T minus Fr will be equals to M1 times acceleration. Now, if that's the case, then we have that T minus mu M1 times G equals M1A. You know what this is? This is our normal reaction. This is the coefficient of friction. Now, so call this one equation 1. And for equation 2, which is this one, we have that M2G minus T equals M2A. So, what do we do here? If we actually add the two equations together like we did the other time too, we'll have something like mu minus mu M1G plus M2G equals M1 plus M2 into bracket A. I mean, we have A here. So here what do we have? We have, now there's something here again that we need to take note. Although let me quickly derive this formula generally, and I will now come back to what the question is saying. I'm looking for mu. So if I'm looking for mu, then that implies that mu M1G, unless I'm taking it to this side, will actually be equal to M2G minus M1 plus M2A. Now, this implies that mu M1G equals M2G minus M1A minus M2A, and I think M2 is common here, so we have mu m1g equals m2 into bracket g minus a, then minus what? m1a. Now, since I'm looking for mu will now be what? m2 g minus a minus m1a over m1g. That's what mu will be. Now, generally, this is what our mu will look like. But this case, the objects, they were on the verge of sliding, which means that they did not start sliding, which means that there is no acceleration. So since there is no acceleration, then we can say that acceleration equals to 0. So at every point we see acceleration, we will put 0 there. So this will now be equals to m2g alone. Then minus this will be 0 over what? m1g. And by the time we do that, we see that this will be what? m2 over m1. So the coefficient of what? The coefficient of static friction between the mass m1 and the table is m2 over what? m2 over m1. That's that. Let me quickly say something there. It's something very, very amazing. Let's say I've not removed this g. We will have that m2g equals mu m1g, which implies that the weight here is actually for a body that is not sliding on this kind of surface. For the body that is not sliding, which means that the weight of this body will actually be equal to the what? Will actually be equal to the frictional force that this body will experience on this surface. So that's just it. Now that's the end of that question. Now let's take one more question.